Thank you. Good afternoon, folks. Welcome to the session on PFAS monitoring, analytical methods, and data confidence. And we have a good line of speakers, and it all falls in place with different speeches this afternoon. So the first speaker is Paul Jackson, and he will be talking about biosolids analysis of PFAS, challenges, considerations, and options. And currently, there is a biosolids a round robin going along at ASTM D19 committee, which Paul Jackson and his team are also performing on. So it's an apt topic. And here is Paul.
Thanks, appreciate it. And as I said earlier this morning in my presentation, thanks to the forum for inviting us to participate. This was an interesting segue because our presentation this morning, Lucas and mine, was about NPDES, so biosolids is just marching down that path a little bit further. I'm going to pay very special attention to that clock on the floor to make sure I don't exceed my time limit. And I'll skip through a couple of these intro slides. This is our corporate PFAS team. The 6 of us cover the nation, and all we do is help our clients and our labs make sure that we are doing PFAS projects correctly, given all the different matrices and reporting limits that we're seeking to achieve these days, especially given the ever-evolving regulatory climate that's changing rapidly. This map, the green and the blue dots, are all of our environmental labs. The blue dots are our labs that provide PFAS testing in addition to other environmental matrices and analysis. You can see one blue dot here in Florida, right up the road in Ormond Beach. This lab was actually our first lab to put PFAS testing online years ago in UCMR 3, which took place in the nation's public water systems from 2013 to 15. These are the topics I'm going to cover. Some of these things are pretty basic about biosolids and its history, so I'll gloss through that pretty quickly because I want to get right into the meat of the biosolids challenges that we are seeing with EPA 1633. Some of the basics about biosolids and its regulation, good old Part 503, that's what we've been working with forever, that regulates the standards and the limits for land application of wastewater treatment plant sludge, obviously to protect human health and the environment. What's the definition of biosolids? It could be solid, semi-solid, or liquid residue generated during the treatment of domestic and industrial wastewater treatment plants. A little bit of a foreshadowing of what I'm going to get into with the EPA 1633 slides. It's the low solids biosolids that are the real challenge in that test method. That term biosolids, it reminds me of water reuse in the state of Florida, since we have purple pipes all over the state for wastewater that has been treated to drinking water standards so it can be land applied for irrigation. The term sludge predated the term biosolids, but that's a pretty unsavory term, so the industry and US EPA adopted the term biosolids. But they are synonymous. Most of our clients use them both interchangeably as if they're the same, and that's essentially what they are. 3 forms of biosolids. There's solid, semi-solid, and liquid residue, or low solids. And when I say low solids biosolids, the analytical challenge starts at about 5% solids and less. But more about that later. There's 2 classes generally accepted, Class B, Class A. Class A means no pathogens, simply put, and therefore that may be applied anywhere, including in public areas. But it's that last bullet that's the kicker. Why are we talking about this? Why do biosolids contain PFAS? We've been accumulating a lot of evidence in just the last few years, partly due to US EPA's ELG 15 study. Obviously, industrial wastewater discharges contain PFAS, and it varies dramatically from industrial classification to other classifications. Also, wastewater treatment plants frequently are accepting landfill leachate. Well, this crowd, we're all PFAS pros. We know that landfill leachate is pretty much universally hot for a long list of different PFAS, including precursor chemicals. Also domestic wastewater. There have been recent studies that have shown evidence that yes, domestic wastewater, i.e. wastewater that does not include any industrial discharges, so it's what we do in our homes, can also contain PFAS. For example, you see in that bullet right there, that the source seems to be primarily revolving around us washing our clothes that contains stain-resistant, water-resistant chemicals. The last bullet, that's very important. EPA discovered in ELG 15 that it was frequently finding higher levels of long-chain measurable PFAS by EPA 1633 in wastewater treatment plant effluent after treatment than in influent. Obviously, the source is the short-chain precursor chemicals, and there's a very long list of those, many of which are not included in EPA 1633 or other compound-specific methods. This is a very troubling revelation. So what is the case against land application of biosolids? Starting with the good old state of Maine. This is a very well-known topic, lots of headlines going all the way back to 2016. Maine is a dairy state, big dairy producer, and they first discovered a link between biosolids and milk way back then. And as you can see in the second bullet is a pretty dramatic finding in that the state of Maine detected levels of PFAS in some milk samples, thousands of parts per trillion. Obviously a very big concern. That led in 2019 to Maine regulators doing a large-scale study. One of the findings was they found lots of PFAS in neighboring private wells to contaminated farms that had used land-applied biosolids. That led in 2022 to Maine banning all land application of all biosolids. A gigantic shockwave to the state's wastewater treatment plants that suddenly obviously had a big financial hit to dispose of all of that sludge when they couldn't land apply it. Oh, and by the way, the state of Maine does not allow landfilling of any biosolid or sludge either. So 100% of the state sludge is being shipped out of state for disposal. Obviously, a lot of litigation has transpired. That's going on around the country as well. Washington, Oregon, Wisconsin, Virginia, New Hampshire, Maryland is a recent addition to this list, have taken measures to restrict or ban land application. First bullet, this is a University of Michigan study. U.S. publicly owned treatment works generate about 14 million tons dry weight of sludge annually, a lot. Disposal options are limited. There's landfilling, there's incineration, land application. Those are the three sources of disposal of sludge. And obviously, land application has had great benefits to the agricultural industry because of fertilizer, and it's clearly the least expensive option. So what's going on at the federal level? US EPA. January of 25, EPA issued its biosolids draft risk assessment. A great document. It found, no mystery here, that PFOA and PFAS in particular, contamination of biosolids warrants its setting limits on discharges from several industrial categories, including obviously PFAS manufacturers, electro and chrome platers. They don't use PFAS as a part of their product production. They're using it in their process to control mist. So lots of different applications for PFAS. That's just one of many. And obviously landfills. So review of public comments is now ongoing for this draft risk assessment. It's taking much longer, just like everything else has at the current US EPA, I think partly due to dramatic cuts in staff. What's going on at the state levels? State action. Dark green states they have adopted restrictions and measurement and starting the process of setting numerical limits for PFAS and biosolids to be land applied. Light green states have introduced legislation or regulation, but this map keeps changing because just in the last 3 weeks, the governor of the Commonwealth of Virginia did pass legislation that had been passed to start a tiered process of restricting and measuring PFAS and biosolids. Maryland almost immediately followed suit because they both contribute to the Chesapeake Bay, and that leads to them acting in concert. Notice the state of Florida is gray. That's now out of date too. Because the Florida House, as I said earlier this morning in my presentation, the Florida House, the Florida Senate, this past session introduced identical legislation to start studying and controlling PFAS in wastewater treatment plant effluent and in biosolids. So let's get into the lab rat weed stuff, the nerd stuff that us lab folks like to talk about. This is the challenge when it comes to the use of EPA 1633A to analyze biosolids. EPA wrote a process in 1633 that tells us when we're analyzing biosolids versus another solid like soil, that we use 1/10 of the sample volume. So what does that mean? Especially when we're analyzing a low solid sample. All the guidance that's being rolled out in the various states, in addition to this, tells us that we should analyze a biosolid sample as received. As received, what does that mean? That means that when we have a very wet sample, we're not supposed to separate the fractions and analyze them individually, although there's still a lot of ongoing debate about how to deal with this topic, because EPA, when they supposedly made 1633 final, did not tell us exactly how to deal with this in the lab. So that's the challenge. It also says that we can extract a maximum of 10 grams as received. So the challenge continues, and then we have all these other steps to go through in the process, more steps to go through with a biosolid sample, and the example is a 5% biosolid sample. 2 more extractions of the solid sample, 15 ml methanol, followed by another 5 ml methanol, equals 20, and then we bring the volume of the combined supernatant up to 75 ml. Extract again using solid phase extraction. Complicated process. But getting on to some of the minutiae here and how it pans out in terms of reporting limits. This column is our typical reporting limits for those compounds in a soil sample in micrograms per kilogram. These are the reporting limits for a biosolid sample because, again, 10x, because we're using a different sample volume. So lots of challenges. The problem statement, we decided to do a study to compare 1633 to another test method that's available now to us, and that's ASTM-D 8535. When we're dealing with a low solids biosolid sample, 1633 is challenging to use for those reasons that I just described. So we wanted to compare those two methods to see how they both performed. And this further details the challenges. So these were our goals in our study. We wanted to determine the limits by 1633 in a low solid sample. We wanted to compare those results to the ASTM method. We wanted to use multiple sources of liquid biosolids. So industrial sources, solid waste sources. We also wanted to do an inter-lab comparison study. We didn't want it to just be PACE Analytical's data. And here's some of the results very briefly. So these are the characteristics, and there's a compound list here. We're going to focus these results just on those compounds. You can see PFAS and PFOA are there at the bottom. We took a 1.4% solid sample. We analyzed it by ASTM-D 8535. These were the results in this column. So they're kind of all over the place. But this is the column to focus on, the EIS percent recovery levels. And as you can see, every organics method has an EIS recovery range that can vary widely depending on the method. The closer we get to 100% recovery, the better the QC data in simplistic forms. And as you can see, very close to 100% by this method. 1633, here are the results for the same sample. You can see there's some differences. And one very interesting question that I got in a presentation on this topic a few weeks ago at the Virginia Rural Water Association conference was, with data like this, if we're allowed by our regulatory agency, if we can get lower results consistently by one method versus the other, should that be the method we choose? And that's a great question, one that I can't answer really. That's more of a regulatory agency question. But again, focusing on the EIS percent recovery, you can see 1633, acceptable range, so good quality control. It still passes, but not as close to 100% as the ASTM method. So we were encouraged by this. We worked with EPA on this study. So this data is from an EPA study of the same topic. They went at it a slightly different way, and they chose to spike the same low percent biosolid sample, 1.4% solids, with different PFAS levels. As you can see, in the far left column, spiked it with 3.6, the middle column with 28.5, and the column on the far right, 57 parts per billion. So different levels of spiking. And you can see the EIS percent recoveries, all, again, very good. So we were very encouraged by this. A great set of pictures that shows what we are frequently dealing with in the lab. As you can see on the far right, these samples are frequently sticky goo. So that adds to the challenge, obviously. So I'm finishing early. Yep. And in conclusion, when it comes to complicated matrices like biosolids, you really can't over-communicate with your lab. We really need to know as much as possible about these challenging matrices. We also find that in the environmental world, that frequently biosolids aren't even a matrix code on a chain of custody. So when, for example, I told you I was with Virginia Rural Water Association a couple of weeks ago, these are wastewater treatment plants that are generating biosolid samples to us constantly for PFAS analysis. And many of the treatment plant operators, they're just used to writing in solids or the word sludge. Sludge is not the word that's in EPA 1633. If the chain of custody doesn't specifically say biosolids, we're not going to use the correct sample volume. So that's really important. Obviously, you want to communicate the total solids if you can, even if it's not biosolids, because TSS is a challenge with 1633 sometimes. You want to communicate your goals, your limits. Is your regulatory agency telling you you must meet numeric limits when it comes to biosolids and wastewater and non-drinking water matrices? FDEP is a great example of a state that's not yet doing that. But they're intent on collecting information that will enable them to do that. That is the purpose, I think one of the main purposes of the wastewater and biosolids legislation that's currently on Governor DeSantis' desk to sign. They want to spend the next year after this program starts to collect this information about the levels of PFAS in the state's municipal wastewater treatment plants and the levels in biosolids that are meant for land application, and then develop regulation to deal with this thereafter. And that's it. Thanks, everyone.
Thank you, Paul. That was interesting on the comparisons between the biosolids ASTM versus 1633. We'll hold off the questions till the end of all the conversations, so we'll get some time accumulated at the back end. So the next presenter is James Mills. He's going to be talking about building a dynamic conceptual site model using 3D visualization at a complex PFAS site. Please welcome James Mills. Thank you.
Hi, everyone. So this presentation today will include a high-level overview of a 3D visualization and explore a case study at a PFAS impacted site using Leapfrog Works. We'll first take a look at the overview of 3D visualization, including benefits, limitations, timing, and alternate applications. We'll then jump into the case study, and we'll take a look at the site overview, the visualization overview, input, several use cases, and potential next steps. Just a note on terminology, I may use 3D maps interchangeably with visualization, just because it's a mouthful. All right, so we'll move on. Looking at the benefits of 3D visualization, first, they enhance understanding. They integrate factors such as geology, groundwater elevations, and chemistry into a single comprehensive model, which we can use to visualize subsurface relationships that might be easy to miss in 2D. This can lead to stronger, more defensible conceptual site models. Second, they support better decision-making. 3D allows us to test ideas visually. For example, we can evaluate whether a plume is fully delineated, where contaminant mass is stored, and which intervals might be important for remediation. Third, they improve communication. Traditional 2D figures can rely on mental reconstruction of complex 3D subsurface conditions. This can result in miscommunication or inconsistent interpretations. 3D creates a cohesive site interpretation which enhances understanding of site conditions, reduces misinterpretation, and makes uncertainty explicit. Finally, they can promote efficiency. 3D maps can assist with identifying data gaps and reducing unnecessary fieldwork, which ultimately can save time and money over the life of a project. The real benefit of 3D is not necessarily prettier graphics, it's that they help us integrate diverse data types to promote better decision-making, improve stakeholder communication, and more defensible outcomes. So to be fair, and as with any tool, there are some limitations as well that I wanted to bring up. So early on in site assessment, you may be working with limited data sets, and 3D maps may not necessarily reduce uncertainty, but exaggerate it if you're interpreting limited data. Second, they require time and effort, and that comes with project cost. Defensible 3D models can require skilled staff, specialized software, training, and licensing, to name a few. These factors may lead to initial higher project costs up front, but you may be able to recapture those costs over the life of a project by reducing unnecessary fieldwork. Third, they can foster false confidence if used too early with limited data. 3D maps require assumptions, and those assumptions may lead to overinterpretation with limited data. The end result could look polished, but it may create false confidence in interpretation that has limited data. Fourth, models can be persuasive. Once a surface is visualized, stakeholders may become anchored to that initial interpretation. This makes it harder to pivot when incorporating future data. Also, it can create stakeholder expectations that the system is fully understood and may lock stakeholders into premature interpretations. However, with the use of strategic timing, you can overcome some of those limitations, and it can aid in stakeholder acceptance rather than create unnecessary distraction on your project. So when should 3D be used, and should you use it from the onset of a project? Generally, we found it's more effective to let the project mature and collect additional data. And as the uncertainty starts to narrow with increased data collection, then you can use 3D to enhance your decision-making. You can use it on projects to assist with questions like, are we fully delineated vertically and horizontally? If not, where do the major data gaps exist? Where is the bulk of contaminant mass stored? and what intervals might be important for remediation. Are project decisions defensible? I did want to point out a few alternate applications. We're going to be taking a look at a case study that uses just one of many different types of applications for 3D. So, and these may be of interest to you in the audience today. In terms of environmental assessment, you can couple maps with extensions such as ModFlow for contaminant fate and transport modeling. You could use 3D for high resolution data sets. Let's say you have a lot of MIP data or DPT data, a lot of dense data sets. Works really well with 3D. For remediation, you can demonstrate the effectiveness of a treatment by tracking the plume over time. You can also use it to prepare in your remedial design in looking at contaminant volumes or mass estimates. Lastly, for stakeholder communication, you can use it to demonstrate complex subsurface conditions to non-technical audiences, and you can think about a setting like a public meeting. So now we're going to move away from that and jump into the case study today. We'll first start with an overview of the site. This site is impacted with, has PFAS contamination in soil and groundwater due to the release of AFFF. And to orient you a little bit, I know there's a lot going on that figure, but the orange boundary, the orange rectangle on that slide, represents a site boundary. The source area is roughly depicted in that red oval. And since about 2019, we've collected 62, or we've installed 62 monitoring wells and collected 49 grab samples at different locations across the site and off-site, I should mention. The site is under the FDEP provisional cleanup target levels for soil and groundwater. Today, we're going to be really focused on the provisional GCTL for the summation of PFOA and PFAS, 70 nanograms per liter. That's roughly depicted by the yellow polygon for the overall groundwater plume at the site. The site also has some complexities, which I wanted to talk about today. So in terms of the groundwater plume, it's roughly 1.3 miles from north to south and about 0.7 miles from east to west. This represents an aerial extent of about 380 acres, and the plume extends to about 250 feet below land surface. The topography ranges across the site with some roughly over 60 feet from 80 feet above sea level to 140 feet above sea level. There are a number of potable and supply wells within a 1 mile radius of this site, about 360 active wells. And there's a particularly high density to the north and northeast of this site, and we'll come back and revisit that a little bit later on. Also, this site overlays a limestone aquifer with karst features. So this makes drilling challenging. We recently hit a void upwards of 30 feet in the subsurface, but also trying to determine contamination migration pathways in the subsurface. So moving on, why did we go with 3D visualization for this site? Well, ultimately, there was still some uncertainty in plume geometry and vertical migration of the plume, despite having a robust monitoring well network. There was also some uncertainty on groundwater withdrawal offsite from the potable and supply wells within that 1 mile radius. Ultimately, we decided to go with 3D to enhance the client's understanding of the complex subsurface conditions, and also to use it to identify potential data gaps for delineation. We decided to go with a dynamic visualization that we could iteratively update as we collected more data throughout the project to enhance the understanding of the conceptual site model. And overall, we wanted to deliver it with an overall project cost savings to the project. So in terms of the input to this model, we decided to go with Leapfrog Works to combine the data into a single, comprehensive, cohesive representation. And we decided on Leapfrog Works because we had data in an existing Aqueous database, and it worked well with our modeling team's workflow. We decided to start simple with this visualization. I'm about to present on the data that we put in there, and you can see it's relatively routinely collected data during site assessment. So, and the point I want to make with that is you don't need complex data sets necessarily to get started with 3D. You can start simple and build from there. So in terms of our model, we used well construction or sample point details, including things like borehole identification, very, very straightforward. horizontal coordinates, top of casing and ground elevations, well screen intervals, and sample depths. Again, very routine data. For the chemistry, we incorporated the summation of PFOA and PFAS, and we incorporated data collected since 2019. So this represents a data set of about 220 groundwater samples. We incorporated a recent groundwater elevation data from 2025 and some publicly available data, including a digital elevation model and aerial imagery. Again, the main idea here was to start simple and build from there as the project progressed. Now we'll take a look at some of the use cases for this model. We'll present a total of 3. We'll first start with this use case, and we really wanted to visualize the potential impact of groundwater withdrawal from potable and supply wells on the northern boundary of the site. Again, there was a high density in that north to northeast portion off-site, and so we wanted to take a look at that. Our main question we were trying to address was, are there data gaps in vertical and horizontal delineation in this area? So the area of interest I'll be talking about for this use case is highlighted by the red oval on this slide. And when we zoom into that area and look at the data, we can see that there's an increasing PFOA and PFAS concentration trend with depth. So as we get deeper in the subsurface, the PFOA and PFAS concentrations are increasing. So we used the 3D model and we took a slice, and this is not the entire model, but just one slice of it. I do want to point out some features on this since it's not labeled on this slide. The blue symbols represent existing monitoring well or grab samples. So the grab samples are indicated by the smaller of the two, and the monitoring wells are represented by the larger of the two. We have the 70 nanogram per liter PFOA and PFAS contour line, which is highlighted in that light yellow. We have the pink, which represents proposed sonic profile sample locations, and the purple, which represents a proposed monitoring well. So now we'll take a look. We'll rotate this in 3D so you can see the different angles of that plume. And so what were the outcomes from this use case? Well, we used the 3D map to propose sonic profile samples and a monitoring well location, as you can see here on the slide, to evaluate the vertical migration in this area. The 3D map provided us with a simultaneous view of horizontal and vertical plume geometries that could be rotated in space. It also provided transparent justification to the client and supported our proposed screen interval selection. Second, we'll take a use case that we use this model for was looking at the length of the plume and looking at the north to south axis of the plume. We were really interested in looking at borehole identification within the plume itself. So the main questions we were trying to address with this was, do we understand the impacts along that north to south axis of the plume? Is this a continuous plume or are there multiple plumes? That plume, again, is outlined on this 2D this 2D site plan in the yellow polygon. And the area of interest I'll be talking about for this use case is highlighted by that red oval. So immediately when we take a look at the 3D visualization, and this is a site plan from that visualization, we can see that it interpolates it as discontinuous plumes, 3 to be exact on this slide. There is one that's not shown off-site, a little bit further south. But so we have discontinuous plumes, and so this was a data gap we needed to explore a little bit further. So now I'm just going to show you 2 different views from the model as well, cross-section and an oblique view, and it becomes apparent that we needed to install a cluster between these 2 plumes to evaluate, what's going on. So ultimately, we used it to recommend a well cluster, which I have highlighted in that red rectangle. And this was an example of where we used it to make a defensible decision and present that to our client where some uncertainty existed. All right, this is a final use case, and now we're going to take a look at the source area. So we were looking at the boundary of the plume, within the plume. Now we're going to take a look at the source area itself, and that's depicted by the red oval near the eastern boundary of the site. The main question we were trying to address here was, are there elevated concentrations moving in discrete intervals off-site? So this is another slice of the 3D visualization, and before we move on, I did want to point out two additional features. One is that longer blue rectangle. That indicates an existing supply well, and this is a supply well that's off-site. The other thing I wanted to point out is that red contour, which indicates 100 times the provisional GCTL, or 7,000 nanograms per liter. So that's really going to be the focus of this visualization. Now, if we strip those other contours away, we can really focus on that high concentration area when we rotate it. So by reducing the view with this cross-section and focusing on the highest concentrations only, we could easily identify data gaps between the on-site source area and the off-site supply well. This helped us visualize and communicate to the client where high concentration contamination might be migrating and propose sonic profile sample locations and monitoring wells to attempt to address these data gaps. Ultimately, this helped us strategically place those locations to evaluate migration pathways. Okay, so that brings me to the end of the use cases. Where do we go from here? Well, we'll continue using the model and iteratively updating it as we collect more data, as we install more wells and collect more groundwater data. And that'll be our main focus of using the visualization. We could potentially use it if long-term monitoring is considered at this site to optimize groundwater sampling, not only the network, but the frequency, to help save on project costs long-term. We could use it for risk assessment purposes. We could couple it with extensions such as ModFlow to look at fate and transport modeling, particularly with those off-site potable and supply wells. If remediation is considered for this site, we could also use it to evaluate mass estimates and volumes in the subsurface. So some key takeaways I'll leave you with today. One, 3D maps can provide defensible decision-making tools when introduced with sufficient data and used iteratively during assessment. 3D maps can focus collection of future data by highlighting areas of uncertainty, leading to increased project efficiency and saving time and money over the life of a project. Lastly, 3D can enhance stakeholder communication and understanding. Thank you.
Thank you, James. Our next presentation will be by Ms. Tonya Chandler. She's going to be talking about electrostatic concentration of PFAS in complex waters concentrations, and then evaluation of the BioLargo Aqueous Electrostatic Concentrator, AEC technology. Please welcome Ms. Tonya Chandler.
Good afternoon. It's always a challenge to be a presenter after lunch. So, wake up. Oh, come on, guys. Do I have to tell a joke to get you guys to liven up a little bit? Okay. Why do PFAS never get invited to parties? Because they never leave. All right. I'm going to talk about aqueous electrostatic concentration. I got to wake you up for this. It's not as hard of a concept as it sounds, but it is one that basically uses the polarity of the PFAS against itself. So we're going to talk a little bit about how we did this. We're going to study the scope. We're going to talk about kind of the methodology we used, go over some of the results, and then I'll show you some of the lessons learned at the end. And I'm going to try and make this not sound like a sales pitch. So let's talk a little bit about the history of AEC. The AEC was actually started as a call for innovation by the US EPA. They were looking for different methods to remove PFAS from water. Our engineers got together, they thought about using one of our other technologies and then realized, well, if you had already gotten grant grant money for it, it didn't qualify for the SBIR grant, so they designed something new on the back of a napkin, literally while they were sitting at lunch. It was technically a failed experiment. Everything that you're going to see here was against what we originally thought the hypothesis was going to come out. We totally thought that we were going to concentrate it in side chambers and that we would have to find a way to get rid of it. You were going to end up with a concentrated stream. That's not what happened. So this was a failed experiment, just like 88 years ago, PTFE was a failed experiment. And if they just would have left it sitting on a shelf, we wouldn't be here today. And our engineers are geniuses, but we don't tell them that. So we all know where we're sitting right now. You've got the 4 parts per trillion for PFOS and PFOA. There's these 6 other PFAS that sit out there somewhere, 4 of them being regulated under the drinking water regs. Don't count them out yet. I know y'all read the story last week where they were talking about pulling them back. Don't count them out. And these technology and the new technologies are emerging, okay? We've got our standard traditional technologies. We've got GAC, we got ion exchange. Don't count out the emerging techs just yet. So how does it work? Because that's the question, right? Does it work? So let's talk about it. So in our unit, and I'll show you a picture of one in a minute. In our unit, we have 3 chambers on the inside of it. The chambers are separated by membranes. So let's see if I can find the chambers are separated by membranes. Those membranes, the one on the chamber 2 side doesn't do a lot. It's there primarily for the future because most of the PFAS that we work with are going to go towards your anode, right? PFAS migrate naturally towards an anode. So what we did is we created a chambered unit, we put an anode on one side, we put a cathode on the other, non-sacrificial. They never touch the water, but they create this electrolytic field across that module. And as the PFAS come in, they naturally migrate towards that anode. The electrolytic draw enhances that migration towards the anode, and then they hit the membrane, and they fuse there. Now, my chemists hate when I use the word fuse because they say that's not actually what happens, but that's the best way to understand it. They fuse there. And when we backwash the membranes to clean it, those PFAS don't come off. But they create these beautiful little caterpillars across the surface of that membrane, meaning that that membrane has an exorbitant amount of capacity. So typically the modules so far that we've found can run for over 2 years. We don't hit capacity on them, but what we do find is that after about 3, you're going to start getting a little bit of electrolytic degradation on that membrane. So what we're actually getting is PFAS migration, ion separation. The rest of the ions go into those side chambers and we blend it back into the water. If you were to take what we call that capture process chamber, that main chamber, and measure the water coming out of it, you would get about 5 microsiemens or less. All of the ions are in those side chambers, so we need to blend them back so you actually get balanced water, and it becomes selective PFAS removal. Now, we do have the ability to take those side chambers and do a mixed blend for people, but that's not what we did in our actual case studies. So we recombine the side chambers, and you get selective PFAS removal. So the concept started with some metal plates, some membrane, and some clamps. That's what it looked like when we did our first studies. Slowly over the course of time, we've been able to figure out how to size these up. One of the hardest things when you talk about case studies on emerging technologies is everything works great at a bench scale, and then you have to size them up. And there is unique steps and unique challenges on each step in sizing up a technology, especially like this. So we wanted to make sure that when we were doing this, that we tested all different water matrices because all matrices react differently. So we did some surface water testing, we did some groundwater remediation testing, we did RO concentrate, and then as our experiments progressed, we started in on things like landfill leachate and industrial water. We always use 537.1 and 1633. Before a lot of the labs started testing with a detection limit below 1 part per trillion, we had actually started working with the University of Tennessee, who were able to recreate it below 1 part per trillion consistently. We did most of our work at bench scale and then sized up to about 1 gallon a minute for the testing that you're going to see in a trailerized unit. We did work with controlling parameters like temperature, conductivity. We did test, what you're going to see is the inlet and outlet. If I started going through all the data that we did, your eyes would bug. Each set of samples that we did had 12 to 14 samples that went into the lab every time. And then, of course, field blanks and all of that. So, did it work? Well, you can see by where we started out where our goals were. So we started out with the water that came in from California, which was RO concentrate. That goal was 70 parts per trillion. And it was on each analyte, it wasn't combined yet. So that was very early in the process. As we moved forward and got into Wisconsin, then we started looking at getting down to non-detect. And I'm gonna go through these pretty fast because everybody gets a copy of it at the end, so. As we started looking at surface waters, we actually started finding more challenges. The more you start dealing with surface water and industrial waters, you're dealing with other constituents in the water. What we found was in surface water, in lagoon water, the organics didn't bother the membranes at all. A lot of the solids would flow right through the system without any issues. Industrial groundwater wasn't really an issue, although this is New Jersey water, and I now think people in New Jersey are pickled instead of when they drink their groundwater, because this was consistent in a lot of the New Jersey water that we tested, that they're in certain parts of New Jersey, they're up over 1,000 parts per trillion. So if you vacation in New Jersey, drink bottled water. But we were finding that on the industrial groundwater, we were coming across smaller chain PFAS. We did some work where we were actually removing ultra short as long with the short chain PFAS. So what you're seeing here is kind of a cross section of some of the work that we did. As we started looking at the matrices, we found something very interesting in this system. We found that conductivity and PFAS removal mimicked each other. So we were able to actually watch the percentage of PFAS removal by actually watching the conductivity removal, which made it really easy to realize then that we could actually watch the membrane saturation. So we knew when that membrane would actually start hitting that point where it wasn't doing its job anymore. We were also able then to realize that we could tailor in that system for what type of removal was needed. If somebody didn't need 100% removal, we were able to kind of tailor that in. And the temperature allowed us to ensure that we were getting the correct performance in the water. We took all of those and we moved it over to leachate. Now, leachate created a whole different challenge for us, because not only were you dealing with the PFAS in the water, now you were dealing with things like volatile organics. And that took a little bit more of a stepped approach. You had COD, you had more hardness, you had more conductivity. And one of the things that we were finding out is that as we started doing this, we were looking at a total analysis. So we started looking at, okay, if we're going into leachate, where do we have to have our performance matrices come out to be competitive against the traditional technologies like foam fractionation, RO ion exchange combinations. But first we needed to just take on that challenge. So what we ended up doing and what you see on the bottom is more of a 4-stepped approach to PFAS removal. And that was, we would actually do a process, it's a unique type of coagulation flocculation. The PFAS is actually staying in the liquid. Don't know how they do it. Again, I told you my engineers are genius, but they don't tell us, so we can't tell anybody else. So we do that unique coagulation flocculation process, then we run it through a process if we need to lower those VOCs. And that's just to protect that membrane process that's inside of it. Then we run it through the AEC. And then when that membrane hits saturation, usually about a year to 2 years in, that's when our destruction process would come into play. So as we did all of our testing, we're like, hey, great, we are an efficient collector. We need to know, we know how to do this now, but the rest of the industry is going towards destruction. So what do we do? And what do we do with these membranes at the end of this? Because we're just the same as carbon or ion exchange, where there's something to get rid of at the end. Yes, it's less, but there's still something to get rid of at the end. So there's where we talk about what has to be done in the system. And we'll talk about the rest in a minute. This is where we're looking at, we realized that we could actually do other removal with the system. So we realized that the system could remove chlorides, the system could remove potassium, it could remove calcium, it could remove magnesium. But we also realized that it could remove ultra shorts. We were actually removing TFA. We had somebody come to us in one of our pilots and they said, hey, we have some really short PFAS compounds and nobody's been able to remove them so far. Could you try? And we're like, sure, why not? And we were able to remove them. Now, we still don't know what all of those compounds were because they didn't let us do the analytical. We ran the test, we sent it back to them and they said, thanks, you were successful. So we still don't know exactly what all was in that water. But as I said, then we needed to talk about how do we take this to the next step? What was the next step of the process? And so what we were able to do is figure out how to take the membranes that we have and strip the active surface off of them. And then we actually followed it. We partnered with a company that made incredibly efficient EO. And we did the destruction through an electrooxidative process. And we were able to actually take the PFAS and get it down to inert salts. So that meant that the system in its two-step process had no waste. So I'm not going to actually go through this because this is just kind of gives you an idea. The only reason that I do this is to show you that the energy usage can be comparable. As part of our process, we wanted not only low waste, but we also had the goal of being energy efficient. While we're not the most energy efficient technology on the planet, I won't pretend that. When you do the overall life cycle cost, we were able to come up with a pretty comparable process. As part of our study, we did the economics. We didn't want to go out to market with something that was standard and then all of a sudden had way higher costs. So we did do comparisons against carbon filtration Now, before anybody says it, when they look at these numbers, yes, I know this is an actual average. This is not, some people may pay more for carbon, some people may pay less for carbon. So the analysis was just based on an average done by the EPA in a comparable cost. And then we did the same thing with a leachate system, and I'm not going to go through all of that yet because I want to talk about our first install. Because we actually had just recently had the pleasure of actually not only taking this from a bench scale to that larger pilot, but we now have actually taken it to a full-scale installation. That's what the full-scale unit looks like. These were the compounds that we were working with. So we were, again, in New Jersey, and there was a lot of short chain along with the long chain. Some pictures of what the install looked like. But I'm actually going to go to the next slide and talk about the lessons learned, because it's not fair to talk about a case study and just say everything went perfect, because it didn't. And we had a lot of lessons learned in the work that we were doing. So the first one was expect the unexpected. So one of the first things that we had happen in our first install was that as they were doing the installation, we had a welder that decided to ground out to one of our skids, and then had a bare wire, and I see him laughing up at the front because, yeah, that's what happened. 240 volts hit our skid. When 240 volts hits your skid, you're basically rebuilding all of your electronics. So we had to, our install got delayed by having to redo a whole bunch of electrical. So always expect the unexpected when you're doing pilots. One of the things that's happening in the state of New Jersey is that even the ion exchange and the carbon systems are fighting with the scaling factors. And we were no different. Although the scaling didn't matter in the bench scale that we were doing, we have had to do a lot more frequent cleanings that we thought, and a lot deeper cleanings based on the calcium in the water. That is easily taken care of up front, and we know to design that in now, but the site was a unique challenge in New Jersey as they had no wastewater outlet on site. So doing any kind of softener or anything meant collecting all of the regeneration water anytime you were doing something. So we are actually looking at right now TAC filters that create a solid out of the calcium. It creates a colloid and lets it slide right through the system rather than scaling. Always plan for extra space again. That was one of the challenges, especially when you are not in control of timelines or layouts. Our install that was supposed to last 9 months lasted 2 years. Not by anything we did. We were a 9-month delay on a permit delay. So it was an expect the unexpected and expect extra time factors. And expect a learning curve. When you're scaling up any kind of new technology, the first one is always the hardest. That has definitely been the challenge here because nothing ever goes to plan. One of the wonderful things that we had come up with the system is not only are we being evaluated by the New Jersey DEP, but the EPA took an interest to this, and the EPA is doing testing right alongside of it, so that by the time we're done with this, the EPA will be, US EPA will be well familiar with the system as we go forward. So it's been some unique challenges. It's been a lot of fun as we go through this to take a new technology from concept all the way through application. But there's been some missteps and learning curves along the way, and we are happy that we are actually ready to be in that commercial space now. So in summary, the system is able to remove, we proved that it was able to remove 99.99% of PFAS, whether you're talking about long, short, or ultra short. The system generated low waste. So as a waste comparison, if you had 80,000 pounds of carbon to treat 1 million gallons a day, our same system would produce 2 pounds of waste. It's, average energy consumption. We did decide as we started going into the commercial realm to do a service exchange model with it to help with the waste and disposal. That's where the disposal test came in. And, we learned a lot along the way. So, thank you.
Thank you, Ms. Tonya. Okay, we'll go to the last presentation before we take questions. The last one is by Ms. Taryn McKnight. She's going to talk about PFAS and water reuse, navigating analytical complexities, and treatment validation for regulatory compliance. Please welcome Ms. Taryn McKnight.
Good afternoon, everyone. Before I dive into this topic, I'm going to poll everyone a little bit to see what our notions or understanding are of a few topics that I'm going to address. So, first question, how many PFAS are there? Just shoot out an answer. What do you think it is? So I heard a lot of people vote for A, or 20,000, or still counting. So, I'm going to dispel this one for you in a minute. Which method will close the mass balance on PFAS? So if you're evaluating PFAS treatment, PFAS in, PFAS out, what analytical method can help demonstrate that mass balance? C, top assay. Any other votes? None of the above. Good choice. And we'll talk all about that today. How about total organic fluorine? Is that equal to a total PFAS measurement? True or false? False. No trues. Good job, folks. 2 out of 3. How about the top assay? Will it indicate what transformation of precursors may take place in the environment? True or false? That's probably the trickiest one. Okay, so I'll tell you the answer to that one now. That's false, but we'll go into that in detail. Okay, so before we dive into the analytical details and considerations, let's just talk about the regulatory landscape that we're operating in, right? This always lets us know what's expected of us, what the liabilities are, and what kind of data we might need to generate to make sure we're in compliance with all of that. So on that question of how many PFAS are there, this is a pretty important one when you're looking to regulate contaminants, is how do you even define those contaminants? And depending on the definition you use, you can end up with calculations like you saw in my first question. If you use the OECD definition out of Europe, that would include over 7 million substances that qualify as a PFAS according to that definition. Here's the thing though, these are theoretical numbers, not actual numbers. So when we're talking about assessing PFAS that could be in our waste streams, we need to be thinking about what PFAS were ever produced and introduced into commerce and therefore could be in the environment. That 7.3 million is just theoretical. Most of those were never created. When we talk about actually produced, we're talking on the order of hundreds, maybe over 1,000, something in that range, at least in the US. And so that becomes really important when we're trying to assess sources and characterizing those sources. And within the US, we have a varied approach depending on the program. So whether it's under drinking water, wastewater, hazardous waste, all of these different programs take a different approach using different definitions of PFAS, using different approach to how many PFAS we're concerned about, maybe from a risk standpoint. And so that's part of that very complex regulatory landscape that influences the type of data we feel we need to generate or don't want to generate, depending on what we're trying to manage at a site. And when we talk about the particular pressures on water reuse considerations, of course we have drinking water MCLs if you're trying to reuse the water for potable water use. So you've got your federal drinking water MCLs and various state MCLs. You've got EPA's guidance on NIPD's permitting for wastewater, and then you have various states moving forward to implement that and actually require the monitoring. We heard about that this morning for Florida. You have EPA's Program Plan 15 and 16 to address effluent limitation guidelines for industrial discharges of wastewater. So we may be seeing some of those materialize in the near future. And then there's EPA's desire to conduct an influent POTW study, all addressed in that program plan. And then a little bit more maybe peripherally related is biosolids. So if you wanted to reuse water for irrigation, that may become a compounding issue. So there's concern about the risk that may be posed from PFAS in biosolids that are land applied. So it could be a compounding issue if there are also PFAS in the irrigation water on those same lands. So becoming more of a cumulative issue that we have to be aware of how we're going to address agriculture. And then there's EPA's destruction and disposal guidance. So if you are going to reuse certain water streams and they need treatment, as you just heard, many of those treatment options are going to result in a product that then either has to be disposed of or destroyed, and then you're going to be subject to EPA's guidance on how to evaluate that. And then for a lot of those things to move forward, the NIPD's permitting, the POTW study, things like that, we're really dependent on having EPA promulgated methods to do that with. EPA attempted to provide a few of those, so we have draft methods for 1633A and 1621, but we really need those to get promulgated for the states to the majority of states to feel comfortable with requiring those in NIPD's permits, and those are being held up. They're not yet promulgated. So that's kind of the regulatory landscape. Now let's talk about those analytical considerations and thinking about how we match the analytical methods we want to use with the questions we're trying to answer. So there isn't a one-size-fits-all here, not by a long shot, and so we need to talk about that wide range of questions we might be trying to answer. Before we do that, though, we need to acknowledge the complexity of the chemistry that we're dealing with. PFAS is this great short little acronym, but it represents a vast family of chemicals with different chemical properties. And so the biggest acknowledgement we need to start off with is we are dealing with polymeric and non-polymeric PFAS. Those are the two main branches you see here. From an environmental human health risk perspective, we've been all but consumed with the non-polymeric branch of that family tree. And it really wasn't until we started addressing PFAS in consumer products or industrial products that brought polymers into the fold. But these are vastly different chemicals that have huge implications for the analytical tools that we have and what we can and can't represent with those tools. Another, of course, complicating factor is the fact that we are dealing with per and polyfluorinated chemicals. That's part of that PFAS acronym. So perfluorinated being the completely fluorinated chemicals that are persistent, that don't have that known degradation pathway in the environment, and then polyfluorinated being incompletely fluorinated. So those are going to transform in the environment. And assessing their presence and their ability to transform and end up as those persistent perfluorinated compounds is tricky. And it's also important when we're talking about our ability to comply with those regulations that are addressing the risk drivers, which are the perfluorinated. And then the last complicating factor is just the breadth of applications of these chemicals. So this is just an example of a lot of the different industries that have benefited from utilizing these very powerful chemicals. But the thing is, these industries were not all using the same formulations. So these represent a lot of different types of PFAS usage. Those processes or products could have resulted in a lot of different types of PFAS byproducts and breakdown products, all further complicating our attempts to characterize them. All right, so now when we get to the point of analyzing for the PFAS, what are our options? We can break these into these three primary buckets. You've got the individual PFAS components on the left. This is what we call a targeted analysis. We know what we're looking for, and we just have to try and find it in the sample. If you don't know what you're looking for, then you have to take kind of a non-targeted approach, and there's a few different buckets there. So there's looking at just the fluorine content of the sample and using that as a proxy for PFAS. And then there's looking for the presence of those precursors, those incompletely fluorinated PFAS that can transform in the environment. Those are the main buckets. There's kind of a smaller bucket up there for the unknowns, and that requires a specific non-targeted approach that's pretty sophisticated, so I wouldn't consider it a main bucket, but we'll talk about that in a moment. All right, so where do we start? With our most conventional tools, usually for compliance purposes, and so we have EPA's 1633A method, and this is a catch-all method for everything that's not finished drinking water. So this is all forms of non-potable water, soils, biosolids, landfill leachate, fish tissue, like I said, pretty much everything that's not drinking water. This method applies to 40 PFAS, and as I mentioned, it's not yet promulgated, but has been encouraged for use by the EPA for several years now. But what does 1633A not cover? So I mentioned it is limited to 40 PFAS, but there are many other different types of PFAS out there, some of more emerging concern. So you have those precursors, a lot of which we have yet to identify. We haven't even put a face to the name yet. There's the ultra short chain PFAS not captured by 1633, those novel or unknowns, and then any polymeric form of PFAS. So none of that is captured in the 1633A. And here's some of the implications of that. So on the left in orange are the 40 compounds that are part of the standard method. On the right in white are many more PFAS that can be detected and analyzed for using something like a 1633A. They just weren't included in the method that EPA drafted. So you've got a lot more you could add. You do have other types of PFAS that require an entirely separate analysis, like those ultra short chain PFAS or some of the neutral or more volatile PFAS. Those require different analytical techniques. But then the question becomes, why does this matter? Why would you want to test for anything beyond the 40 that are part of 1633A? Well, what do you notice about those compounds in orange? Most of them represent legacy PFAS use. And when we say legacy versus modern day, we're talking the difference of 20 years ago and older versus the last 20 years, right? So for an AFFF impacted site, 1633 is excellent. It's absolutely going to identify an AFFF source. But if we're talking about wanting to reuse wastewater, and so then we're talking about modern PFAS uses in modern day manufacturing, that list on the left is going to miss a lot of that. You have to branch over into this list on the right to capture that. So when we're trying to characterize a source and its viability for water reuse, that really starts to come into play. As I mentioned, some of those compounds do require separate analyses, and so now there's a cost implication. So you can't just go throwing the kitchen sink at everything because who has the funds to do that? And so you need to be really thoughtful about what the compounds of concern may be, what are the industrial users impacting this source, and start to tailor a program and what questions are you trying to answer. Are you already at the point where you know you have a problem and you need treatment and you need to evaluate the efficacy of that treatment? We're probably not just concerned about a final effluent for a few regulated compounds. We need to understand the total burden of PFAS going into that treatment system and maybe even a mass balance. So we always want to start with what is the question we're trying to answer. Okay, so when we go beyond the targeted approaches, if we need to understand more about the samples than those known compounds of concern, then we're in that non-targeted space. The first application here is the TOP assay. It stands for total oxidizable precursors. And this is actually just a pretreatment step that's combined with a standard targeted analysis, so something like a 1633A. And what it does is take those precursors that are hidden to us. They're not visible by a standard targeted analysis, so they're back here behind us. And it forces them to convert to their terminal endpoint that eventually would happen in the environment, but we force it to happen instantly in the lab so we can make it visible to us. And when we do that, then we get an idea of how many precursors were hidden in that sample or at that site. So that's the value of the TOP assay. And it specifically tells us those hidden PFAS that can convert to today's risk drivers. So it's not just about understanding some novel PFAS that no one's ever heard of. We're not sure if there's any risk associated with it. It's about understanding precursors that could someday become PFOA or PFBA or things like that that we know will be a concern at our site or in our waste stream that we're trying to use for beneficial reuse. Going one step beyond looking at the precursor burden, we can look at the fluorine content of the sample. So that would presumably identify any and all PFAS that could be present at a site. Whereas when you're just looking at the precursors, that's still a more limited view of the whole family of PFAS. So when you want to look at the fluorine content, you've got a few considerations there. PFAS are organic fluorinated substances. So it is only organic fluorine that would be representative of PFAS. There are also sources of inorganic fluorine. And so you would need to be able to separate those out to get a true representation of PFAS only. And that's very challenging to do. When you attempt to make that separation, you usually compromise on capturing all PFAS. You're either going to lose ultra short chain or ultra long chain or Zwitter ionic or cationic or polymeric PFAS. So in no way do we have an analytical tool to conduct a direct measurement of all PFAS and only PFAS. So these things like method 1621 that EPA drafted for total organic fluorine in water samples is just a rough estimation of more unknown massive PFAS that could be present at a site. It is in no way suitable to be like a risk assessment tool. Then you have the non-target analysis. So this is where you don't have to know what you're looking for at all. You can analyze the sample and scan the results for anything and everything. It doesn't even have to be limited to PFAS. This is a very sophisticated analysis, but probably even more so, it's sophisticated from a data user standpoint, being able to interpret the results. And my first question to anybody who thinks they want to conduct this analysis is what becomes actionable about that data? If we identify for you some very obscure, novel PFAS that are in your sample that you've never heard of, what are you going to do with that information? Because it's expensive and it is hard to interpret. So you have to have a really good reason for this. It's primarily used in a forensic context. So just want you to know it does exist, that it's available. It's just not a primary tool. Okay, so when we wanted to know, we've got all these different analytical tools available to us with strengths and weaknesses. If we applied all of them to something like a wastewater stream, what would it look like? Would some tools look better than others? Would we find a single tool that proved to be the best for characterizing wastewater? And this is how the data shook out. So what you see on the right are targeted results. And we, at the time, our expanded analyte list included 70 PFAS, so that's what's included here, 30 more than what's in 1633. And so you can see the targeted results. Anything that's underlined in red is not part of a standard 1633 analysis. It's not part of that list of 40. And then the concentrations are plotted here on the bottom, and nothing was detected above 35 parts per trillion. So for wastewater, that's pretty benign. Nothing seems alarming about this, and this may seem like an excellent candidate for a water reuse application. But then if you go and apply some of those non-targeted tools, we see a very different picture. So the total organic fluorine, which is presented here as adsorbable organic fluorine because it was applied to water, or the top assay, show that there's a lot more potential PFAS in this sample than what the targeted results are revealing. And so this could have implications both from a regulatory standpoint of those precursors transforming to risk drivers, as well as treatment implications if that total mass of PFAS is running through your treatment system. At another one of the sites, we see a slightly different picture where, with the targeted results, half of the compounds would not have even been detected by a standard 1633 analysis. And the most prevalent compounds would not have been detected at all. So we would have seen a really different picture of this wastewater effluent if we had just looked for the 40 compounds instead of the others. And this goes back to those compounds you see underlined in red that are present. Those are modern day PFAS components, not legacy PFAS. A lot of them are used in kind of surface coating applications. But again, nothing's detected above 30 parts per trillion. Sample seems pretty benign. Okay, let's go run some of those non-targeted approaches and see what we find. Now we see something different. That AOF is showing that there's a significant mass of PFAS present in these samples, but the top assay doesn't corroborate what the AOF is telling us. And so one reason that might be the case is because the top assay is specific to PFAS only. It is not subject to a bias from non-PFAS compounds, whereas the AOF is just an organic fluorine measurement that could also represent things we don't traditionally consider PFAS, like pharmaceuticals, pesticides. And so the literature has demonstrated that an AOF number in wastewater could be as high as 30 or 40% from pharmaceuticals and pesticides, as opposed to, let's call it traditionally defined PFAS. So had we just done what the EPA suggested of a 1633 analysis for 40 compounds and an AOF analysis, we would have seen a really different picture of this wastewater source than if we had run multiple analytical tools. We did also use the non-target analysis to see if we could identify what was making up that large AOF number, and if we could confirm that it was indeed PFAS, and we did not. So what we found was a lot of very low-level signals that would not in any way make up that level of concentration, and just some really novel PFAS that are mostly associated with AFFF applications. So that's how the different tools kind of compared. There's one last picture I wanted to share with you from the top assay data. So you don't really need to be able to distinguish what the different subgroups are that are represented by the different colors. All you need to be able to see here is the difference in composition. So each of these different wastewater sources shows you a very different composition of the types of PFAS that are present in them. And so that speaks to all these different industries, all these different formulations that have been used, and how much we're missing when we just do a standard targeted analysis for 40 compounds, and we don't see maybe the magnitude of and what's really going on with those industrial sources. So when we look at that method toolbox and we attempt to match the tools that we have with the questions that we're trying to answer, this is a bit of a summary for you about the tools we have, the questions that are best answered by those tools, and then what some of the strengths and limitations are in that space, and probably the best use case for those tools. And I don't want to misrepresent that case study where we threw all the different analytical tools that's a pitch for always analyzing for everything. I just want you to understand how your understanding can vary and be so impacted based on the analytical tool you chose to apply. So maybe you want to think about, what do I know about my site? What do I know about my source? And then start crafting and tailoring an analytical approach. And maybe it's a series of tools. So I test for this first. If this, then I do this. And then if this, then I do the next thing. And start to build a workflow there. So kind of your big takeaways here should be that the regulatory demands, not just at the federal level, but also at the state level, really are outpacing that single method approach. And because of that, the approach that you take to a conventional analysis probably needs to evolve from just being one standard method for a standard list, and it needs to be more tailored. And understanding the variability across industry and those impacts to the water that we want to reuse, and what it might take to really characterize and understand those impacts so you can do something and mitigate them. And designing an analytical program that's really fit for purpose. What is the question you're trying to answer has got to be your starting point. So with that, I'm done. Thanks for your time, and are we gonna open it up for questions now? Yeah, all right, thanks.
Thank you, Taryn. So we can now take questions for all of the 4 speakers. So if you have questions, please raise your hand. So you'll get a mic. That should be live. He's going to turn it on. Okay.
This question is for the first speaker, James, I believe. You compared percent recovery using the ASTM method, and I saw that some percent recoveries exceeded 100%. Could you explain why?
That's a great question. The question was, why would a percent recovery exceed 100? That's normal for all organic test methods. There's a percent recovery range that's specific to the semi-VOC method by EPA 8270. I can't recall that range off the top of my head, but they all have ranges, or virtually all have ranges below 100% and above 100%.
Yeah, typically the limits are 70 to 130 is how EPA establishes it, so that's how you see it.
My next question is, I noticed that the percent recovery for the ASTM method over 1633 was greater. Does that make it a better method?
No, and not necessarily. It's kind of, really gets down to the QC chemistry weeds, but closer to 100% is optimal.
Yeah, one example I can give is whenever you have your PCB limits for disposal, that's one of the considerations when you get the recoveries. So whether you're close to that value, like 1 ppm, if your disposal limit is that, then if you have 1.1, what does that mean, right? So that's where that question will come in.
So from a regulatory standpoint, you really need to consider the percent recovery.
It depends. Please contribute to this. But if you're within the recovery range that's written into the method, the data for regulatory compliance is considered acceptable as final data. So it's all applicable for regulatory compliance. Where it gets into the weeds is how in tune do you want to be in terms of accuracy, for example, for a pilot scale study, for a research project.
Yeah.
Thank you.
Yeah, it also is a judgmental thing at that point. So it depends on how the interpretation is done and how your permit is written to exceed or not to exceed, all of those. And when you go through the negotiation on that, make sure to bring up those questions right up front based on your analytical recovery limits. So then everything will be fine right in the beginning.
This question is for Taryn. The first question I had is the total organic fluorine method. My thinking was, there's a lot of that in wastewater treatment. Is that due to because of we fluorinate drinking water, and most of the water that's coming into wastewater plants was started out as drinking water with fluorine, high fluorine content?
Are you asking about fluorination in drinking water?
Yeah, I'm wondering why that indicates a high fluorine content, and whether that TOF methodology is that relevant to assessing the PFAS content in wastewater treatment?
Yeah, so specifically for wastewater, where that total organic fluorine number would come from is primarily any organic fluorinated compound. So that could be PFAS, that could be pharmaceuticals, that could be pesticides. Those are all commonly found in wastewater, and those would all be detected by a total organic fluorine analysis.
So it's not detecting the fluorine itself. It's organic fluorine. Is that right in the analytical procedure?
It is detecting the fluorine itself.
Well, that's my point, is that the fluorine's coming from in with the drinking water.
No, so that's why the isolation of organic from inorganic is important if you want to be representative of PFAS only. And so that's done with a pretreatment step that can isolate that. And then ultimately you are just detecting fluoride. And so that needs to be, that that's organic fluorine because you isolated it from inorganic before you detected it. But
thank you.
But that could also, like I said, organic fluorine could be pharmaceuticals and pesticides as well.
Right, okay.
So what happens in the measurement itself, they do measure the inorganic fluorine and then the organic fluorine as well. So that's how you differentiate it.
All righty. The other question I had was that you talked about the per and poly, PFAS, per and poly, types of PFAS. And my question is, it seems like both of those are degradable, at least. And the tails, I guess I want to make a clarification. The tails of each of those molecules are not degradable, even if they get out into the environment, is my understanding. And the perfluoral PFAS, even the heads of that compound are degradable, is at least my understanding. So
that's right.
I think it's a little misleading to say that one is degradable and the other is not.
So there are different points along the range of chemicals that are degradable and are not. So I can't make a universal statement for them. But if a carbon is attached to a hydrogen as opposed to a fluorine, that's a point for degradation.
But what I'm saying is in the perfluoral substances, the tail, which is all the carbon fluorine bonds, none of that's degradable, even when it gets out into the environment. But both for the heads for both of those substances are degradable, even for the perfluoral substances.
Yes.
Like a carbonate,
so we would call that transformation as opposed to degradation.
Okay. Yeah. Just want to make that point. It seems like, they're not as, they're both biodegradable, is what I was saying.
Yeah.
Would that be?
It could be a precursor too, so
Right.
unless you do the top assay, you won't know that.
But I want to make the point that the carbon-fluorine bond is not biodegradable.
Yeah.
That's why it's here forever, and that's why we're talking about this,
Yeah.
this chemical.
Yeah.
Okay, thank you.
Thanks, everyone. This is Dan again from Aquaga. Tonya, I got one question for you.
Okay.
From one PFAS treatment tech to another. Could you explain a bit more about the membrane, I guess I'll call it cleansing or removal process of the PFAS from there into destruction, and also sort of more details about that and why you ended up selecting EO for that tech, and would another tech be compatible with that concentrated byproduct from your membrane process? So a little bit more detail on that element would be interesting to me. And I'll save my question for Taryn.
Sure. So the removal process is refusing it to the membrane. When the membrane actually gets what we call spent, we take that module back to a facility, we open up the module, we take the membrane out, put new membrane in, it's ready to go back into circulation. But then we take that membrane, we strip the active surface off. There's a patented process to do that, and it creates this goo. We originally chose EO. We have found that the EO has been the best way for the small amount that we have to break it down and break it down fully into the inert salts. We do it in the two-step process so that we can actually watch the chemistry, so that we know we're not off-gassing anything, so that we know we're getting the inert salts at the end and we're not creating any kind of byproducts. We have partnered with some very wonderful companies to do that destruction if we don't choose to do our own process that we started with. If you're asking would it be suitable to degrade in yours or to break it down in yours, it might be. We've not tested it, but it's also in such small amounts that it really does suit well for an EO. Could it go to an incinerator? Yes. We would prefer not to put it back into a landfill. One of the things that happens with a lot of the technologies that we're dealing with, you start talking about landfilling it versus destruction, is if you're treating leachate coming out of a landfill, and then say you're using foam fractionation, you put it into cement, you put it back into that landfill, cement's porous, it's going to leach back out. You're eventually going to short circuit that process, and you're going to do nothing but raise the PFAS levels coming out. So we actually prefer not, what I always call kick the can down the road, and actually take it through a full destruction process. But for us, the reason that we chose EO is because we are dealing with the long chains, the short chains, and the ultra shorts, and EO tends to break those CF bonds in all of them and give us full inert salts, where we can do the mass balance and guarantee that we've gotten most of it. I won't say all, but we've gotten most of it.
No, thanks. And you may have said it, but can you reuse the membranes in the concentrated step once they've been stripped?
We don't reuse the membrane itself because there's such a small amount in those modules, but we do reuse the rest of the module. So it's just the membrane that we strip out. And so I think the actual theoretical measurement is you can treat 1 million gallons of water that contains 70 parts per trillion, and we can do it on 12 grams of membrane. So in a system that would treat 1 million gallons of water a day, you're going to have less than 2 pounds of waste coming out of it. Gotcha. to destroy.
No, thanks for that. Switching gears, if a few weeks ago in Massachusetts there was another PFAS conference, and Mass DEP is running a pilot demonstration with AECOM and others, partners, looking at different types of technologies. And the project scope of that started with compliance with 1633 and targeted compounds, and then it blew up into a lot of different analyses really with the emphasis of looking at the fluorine mass balance and tracking fluorine through the wastewater treatment process. Taryn, my question for you is, have you seen other trends like that across the United States? I know you travel a lot. Like, what's the sort of broad regulatory interest in looking at this topic, fluorine mass balance through the process? And what are the regulators saying kind of as their like next steps? Obviously, regulation of this is a long ways down the road, but maybe just some commentary on that, please.
We do see a trend with an interest in looking at total PFAS. That's usually the way it's referred to. And so right now that tool is assumed to be total organic fluorine by CIC. And so we do see state regulatory agencies being inclined to include that measurement along with a standard targeted 1633 analysis. And that's been the trend for the last few years. We've just recently, I have to wait for we just recently have seen some acknowledgement of the top assay maybe being a more suitable tool for the questions that are trying to be answered. And then now the emerging interest in ultra shorts and tacking that on as an additional analysis.
Yeah, we're getting closer, but I'm not sure we are there on the mass balance question. So like Taryn said, ultra shorts is a very important factor in the whole process because we are missing that because nobody measures it by regulation. So you're measuring from C4 through C14 is all you're doing, and all the regulatory schemes are driven that way. So Office of Drinking Water is considering the C1 to C3 PFAS components, but it's still in the works.
Okay, this is Alauddin Khan, and I'm with Leidos. I have a question for James Mills regarding the 3D plumes that you created. My question is, was the plume created for both soil and groundwater, or was it just for groundwater?
Good question. No, for this particular client, we just looked at groundwater. You could absolutely look at soil as well. We have soil data that we've collected since 2019, so you could look at that too. In fact, for another site that I have, we have looked at that, right, where we've looked at vadose-sown soil, saturated soil. We've also incorporated groundwater data as well, and you can look at those different visualizations depending on what you're going after. In this case, for the other site, I was looking at it from a remedial standpoint and trying to determine, okay, where is my contaminated mass and where do I want to focus my efforts?
Yeah, because my interest was, I think today there was a presentation regarding, the maximum concentration in the groundwater could be somewhere else as compared to where your source concentration is. So I was trying to find out whether you found that based on your soil plume and the groundwater plume, but I guess you didn't create the soil plume.
No, in this case, we're just focused on groundwater delineation and trying to identify some of those data gaps. In the future, if we were to consider additional soil remediation there, we might incorporate that to go after the mass.
Thank you.
Thanks.
By the way, it was a nice presentation. Thank you.
Appreciate it.
Any other questions, folks? Okay, there's Joe.
Taryn, I should probably know this, but is there permitting required for water reuse that people need to comply with some type of level of PFAS for a water reuse project in Florida anyway?
Florida regulations on water reuse for PFAS, not that I know of. I mean, of course, if your reuse application is drinking water, you have to consider that, but for other reuse applications, not that I'm aware of.
Okay. Great presentations, by the way.
Thanks.
Anybody else?
If not, thank you to the speakers and all the questions from the audience. Appreciate it. Thank you.
Two, check 1, 2, 3, 4. 1, 2. One, 2, 3, 4. 1, 2, 3, 4. All right, 1, 2, 3, 4. 1, 2. One, two. So this will be obviously your microphone. Here's your clicker. Forward, backward. You can either look at it on that TV or look here. It's up to you.
Oh, okay.
Because you'll be up
So
here. You'll be up here though. So you can get into play. Yeah. So forward on the clicker. Forward, backward.
Okay.
So we can do. Yeah. See.
So the font is pretty small, I think.
It is. Yeah. It's different when you look at it on your computer screen.
Yeah.
First front and back, or backward and forward?
Forward, backward. Yep.
And the laser?
There is not a laser on this one.
Oh, okay.
Yep.
So this is forward.
Backwards,
Oh, backward,
forward.
forward.
Green, go. Red, stop.
Stop or
You
go
screwed
back.
up.
Okay.
Red, you screwed up. Green, go. Next.
And what's your name again?
Tim.
Tim.
Yeah.
So if something stops, just say Tim.
Yeah. Say, Tim, it's not working.
Okay.
But you'll be good. But you want to stand pretty close, as close to the mic as you can and all that, and I'm sure you'll be awesome.
Okay. I think I can read it from here, probably.
Yeah.
So-
Oh, it's real.
Either one.
That one's, that's what most people look at.
Yeah, but my font
The
is
fonts
not,
on the slides are a little.
not read so properly.
Again, when you look at it on your screen,
I
it's
got
because you're only a foot from your computer screen, so it looks
got it.
bigger.
Yeah. Okay.
How many slides you got? And then we'll have the timer set for 25 minutes, so each of you get 25, and then we leave 15 minutes at the end for questions.
Okay.
If you want to bring your computer up,
Oh yeah, you can read it from
read it
yours.
from there.
Yeah, good thinking. That's why we keep you around.
Okay. Thank you.
Yeah, you can do that too. If you wanna
I've
do
been
that.
at conferences where they don't have that, and people have to look here and so
Yeah.
if they don't have it,
Right.
and read from the.
Yeah.
We actually don't mind it because we record for the camera, and it's picture in picture. So it's you, and then on the record, the picture in picture
Where's
is
the
over
camera
here. Right there, right in the middle.
Okay.
So we just record you, and then we put in the PowerPoint.
Oh,
So when you're looking that way, it looks like you're looking at your screen, because we put it in place of this screen. So we have to do it separate because of the light difference, because that's
Oh, I
bright,
see.
and you would be really dark kind of thing. So it looks good when you look over there. It's not that bad.
So this is water for
You
the.
guys are good? Yeah, there's a bunch. Oh, there was a bunch over there. Is there any left? Yeah,
There's still
one. How many people you got in this one?
I
There
got
3, right?
3 plus me.
I'll have Gene get you another one. Yeah, we'll get one more. So those are.